K3 surface. In mathematics, a complex analytic K3 surface is a compact connected complex manifold of dimension 2 with trivial canonical bundle and irregularity 0. An algebraic K3 surface over any field means a smooth proper geometrically connected algebraic surface that satisfies the same conditions. In the Enriques Kodaira classification of surfaces, K3 surfaces form one of the four classes of minimal surfaces of Kodaira dimension 0. A simple example is the Fermat quartic surface x 4 plus y 4 plus z e 4 plus w w w w 4 equals 0 displaystyle x4 plus y4 plus z4 plus w4 equals 0 in complex projective 3 space. Together with two-dimensional compact complex tori, K3 surfaces are the Calabi manifolds and also the hyperkähler manifolds of dimension 2. As such, they are at the center of the classification of algebraic surfaces, between the positively curved Pezzo surfaces which are easy to classify and the negatively curved surfaces of general type which are essentially unclassifiable. K3 surfaces can be considered the simplest algebraic varieties whose structure does not reduce to curves, or abelian varieties, and yet where a substantial understanding is possible. A complex K3 surface has real dimension 4, and it plays an important role in the study of smooth 4 manifolds. K3 surfaces have been applied to Moody algebras, mirror symmetry, and string theory. It can be useful to think of complex algebraic K3 surfaces as part of the broader family of complex analytic K3 surfaces. Many other types of algebraic varieties do not have such non-algebraic deformations. Definition and definition. There are several equivalent ways to define K3 surfaces. The only compact complex surfaces with trivial canonical bundle are K3 surfaces and compact complex tori, and so one can at any condition excluding the latter to define K3 surfaces. For example, it is equivalent to define a complex analytic K3 surface as a simply connected compact complex manifold of dimension 2 with a nowhere vanishing holomorphic 2 form. The latter condition says exactly that the canonical bundle is trivial. There are also some variants of the definition. Over the complex numbers, some authors consider only the algebraic K3 surfaces. An algebraic K3 surface is automatically projective, or one may allow K3 surfaces to have dual singularities, the canonical singularities of dimension 2, rather than being smooth. Calculation of the Betti numbers. Properties. Examples. The Picard lattice. Elliptic K3 surfaces. Rational curves on K3 surfaces. In contrast to positively curved varieties such as Pezzo surfaces, a complex algebraic K3 surface X is not uniruled, that is, it is not covered by a continuous family of rational curves. On the other hand, in contrast to negatively curved varieties such as surfaces of general type, X contains a large discrete set of rational curves, possibly singular. In particular, Fedor Bogomolov and David Mumford showed that every curve on X is linearly equivalent to a positive linear combination of rational curves. Another contrast to negatively curved varieties is that the Kobayashi metric on a complex analytic K3 surface X is identically 0. The proof uses that an algebraic K3 surface X is always covered by a continuous family of images of elliptic curves. These curves are singular in X unless X happens to be an elliptic K3 surface. A stronger question that remains open is whether every complex K3 surface admits a non-degenerate holomorphic map from C, E, to \displaystyle\math C2, where non-degenerate means that the derivative of the map is an isomorphism at some point. The period map moduli spaces of projective K3 surfaces, the ample cone and the cone of curves, automorphism group, relation to string duality. K3 surfaces appear almost ubiquitously in string duality and provide an important tool for the understanding of it. String compactifications on these surfaces are not trivial, yet they are simple enough to analyze most of their properties in detail. The type Ia string, the type Iab string, the EIX heterotic string, the spin32/Z2 heterotic string, and M theory are related by compactification on a K3 surface. For example, the type Ia string compactified on a K3 surface is equivalent to the heterotic string compactified on a 4-torus Aspinwall 1996. History: quartic surfaces in P3 \displaystyle \math were studied by Ernst Kummer, Arthur Cayley, Friedrich Schur, and other 19th-century geometers. More generally, Federico Enriques observed in 1893 that for various numbers g, there are surfaces of degree 2, 2n, and 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 P G E \displaystyle \math with trivial canonical bundle and irregularities euro. In 1909, Enriques showed that such surfaces exist for all G E equals 3 \displaystyle G \jec3, and Francisco Severi showed that the moduli space of such surfaces has dimension 19 for each G. Andre Weil 1958 gave K3 surfaces their names, see the quotation above, and made several influential conjectures about their classification. Kunihiko Kodaira completed the basic theory around 1960, in particular making the first systematic study of complex analytic K3 surfaces which are not algebraic. He showed that any two complex analytic K3 surfaces are deformation equivalent and hence diffeomorphic, which was new even for algebraic K3 surfaces. An important later advance was the proof of the Torley theorem for complex algebraic K3 surfaces by Ilya Piatetsky-Shapiro and Igor Shafarevich 1971, extended to complex analytic K3 surfaces by Daniel Burns and Michael Rappaport 1975.